Welcome back to Abstract Algebra. Today what I want to do is, first of all, remind you of the statements of the Sylow theorems and then do some examples. So let's get started right away. Remember the definition of Sylow subgroup, of P-Sylow subgroup. So let G be a finite group and let P be a prime. Then P-Sylow subgroup, let's say P of G, is a maximal P subgroup of G. Equivalently, if, let's say, the size of G is P to the n times m, with m some integer that is relatively prime to P, so the largest power of P that divides the order is P to the n, then P-Sylow subgroup is subgroup P of G such that the size of P is the largest allowed as a P group by Lagrange's theorem. So it's a subgroup of order exactly P to the n. And we have already shown that such subgroups do exist. So let's see some examples of this. So for example, if we have z modulus x, then the size of, if this is G, the size of G is 6. So there is going to be non-trivial Sylow subgroups. There's going to be a 2-Sylow subgroup and a 3-Sylow subgroup. So we have that, for example, a Sylow subgroup for 2 would be a subgroup of order exactly 2, and that is the elements 0 and 3 form a subgroup that is of order 2. So this is 0 and 3 modulus x form such a subgroup. And for 3-Sylow subgroup, we're looking for a subgroup of order 3, and that is, well, 0, 2, and 4 forms a subgroup of order 3, and in fact that is generated by 2. So it's the subgroup generated by 2, so 0, 2, and 4 modulus x, those are Sylow subgroups. Let me give you another example. So as another example, let's look at now G is going to be S3. The size of G is also 6, so there's also going to be non-trivial Sylow subgroups of order 2 and order 3. So in this case, for example, for a subgroup of order 2, we can take the subgroup generated by 1, 2. Let me write a parenthesis. So the subgroup generated by 1, 2, so the identity permutation and 1, 2, that is a subgroup of order 2. But notice that there are more. For example, the one generated by 2, 3. That is another subgroup of order 2. So these two are examples of 2-Sylow subgroups of S3. And there are more. Of course, there is at least one more, right? But if we look at z modulus x, notice that this was unique. There was only one subgroup of order 2, and there is only one subgroup of order 3. Here, there is more than one Sylow, and that has to do with the fact that S3 is non-abelian. Okay, so what about subgroup of order 3? A subgroup of order 3 would generated by an element of order 3 would have to be cyclic. So 1, 2, 3 is one such thing. The one generated by 1, 3, 2 is another subgroup of order 3, but it's exactly the same one, right? This 1, 3, 2 and 1, 2, 3 generate the same subgroup with 1, 2, 3, and 1, 3, 2. So this is a Three-Sylow subgroup, but now that is unique. So while we have several Two-Sylows, we only have one Three-Sylow. So the question is, how many Sylow subgroups are there going to be for any given group? And that's exactly one of the things that the Sylow theorems tell us. So let's state the Sylow theorems and then do a more complicated example. I want to do this with A5. So let's first state the Sylow theorems. So the Sylow theorems, traditionally there are three Sylow theorems. By the way, again, these are named after Peter Ludwig Sylow, who was Norwegian, but we typically, at least in the US, we say Sylow. The pronunciation is not good. It should be Sylow, but we say Sylow. In any case, here are the theorems. So let G be a finite group, and let P be a prime. Okay, so the first Sylow theorem, which we have already proved, is the following. Suppose P to the R divides the order of the group, then G contains a subgroup of order P to the R. In particular, G contains a P-Sylow subgroup for all primes P that divide the order of the group. In fact, it contains a P-Sylow subgroup for any prime, except that for those primes that do not divide the order of the group, the P-Sylow subgroup is just the identity element, the trivial subgroup. Okay, so what about the second Sylow theorem? Is going to tell me about what happens if there is more than one P-Sylow. There is a relationship among them. Suppose that P does divide the order of the group, then any two P-Sylow subgroups, say P1 and P2 of G, are conjugate, i.e., there is some G in G such that G P1 G inverse, the conjugate subgroup to P1, is P2. So if I know one P-Sylow subgroup, using conjugation, I can find all the other P-Sylow subgroups. And three, the question is now, how many are there? And it doesn't tell me exactly how many, but it's going to give me some clues. It's a little bit of a puzzle, but it works. Enough information is given that I can try to figure out how many are there. So if P divides the order of the group, and I'm going to call NP is going to be the number of distinct P-Sylow subgroups of G. Then one, let's call it A, NP is congruent to 1 modulo P, so P divides NP minus 1, and B, NP divides, is a divisor of the order of G. Okay, so these are the Sylow theorems, and let's put them to work. Let's use them with an example of A5 to try to figure out all the P-Sylow subgroups of A5. Okay, so let's let our group is going to be A5. I know what is the size of A5. Remember that AN has size n factorial divided by 2, half of the size of S5, and that is 60, which is 4 times 3 times 5. So there's going to be 2-Sylow subgroups, 3-Sylow subgroups, and non-trivial 5-Sylow subgroups. The 2-Sylow subgroups are of order 4, while the other ones are of order 3 and 5. So let's start with p equals 3, okay, which are easier, and let's try to figure out what are the 3-Sylow subgroups. Suppose P3 is a 3-Sylow, then they exist by part 1 of the theorem. By part 3 of the theorem, it tells me, so N3 is the number of 3-Sylows. And the theorem tells me that this is congruent to 1 modulo 3, and N3 divides 60. Okay, but these 3-Sylows, they have to divide 60, and they are 1, the number is 1 modulo 3, so it is not divisible by 3. So out of all the divisors of 60 that are not divisible by 3, that tells me that, well, N3 has to divide 4 times 5, 20. And of those, well, the divisors of 20 are 1, 2, 4, 5, 10, and 20, if I'm not mistaken. And out of those, the ones that are 1 modulo 3 could be 1, not 2. 4 is 1 modulo 3, not 5. 10 is 1 modulo 3, and not 20. Okay, so it has to be 1, 4, or 10 Sylow subgroups. Okay, so how many are there? Well, I have, let's see, let's try to figure out one. For example, well, it has to be a cyclic group of order 3, so I can take, for example, 1, 2, 3. That is one of them. Okay, so I have one. Do I have more? Yes, because I have 5 letters, I have 5 numbers, and I can pick any 5 letters essentially. I just have to make sure that I'm not repeating things, because this one has 2 elements of order 3 are in there. So this is the same one as if I had picked 1, 3, 2, right? So how am I going to count how many of these are there? Well, any one of the 3-Sylows is going to be, well, what are the choices? A, B, C. And I can count, first of all, there is several possibilities. If one is not fixed, then my permutation will start with 1, and then B and C, and I will have 4 choices, because I already know 1 is not allowed, so there's 4 choices for B, and then 3 choices for C. That will be a permutation. We'll deal later with the fact that each one of the subgroups contains 2 of them, so I'll divide by 2 later on. But that gives me 12 choices for permutations that are of order 3 and involve 1, and 1 is not fixed. Now, if 1 is fixed, but 2 is not fixed, then now I know that 1 is fixed So the permutation starts with a 2 and then B and C. And I'm going to have, I know B can be not 4 things, it cannot be 1 because 1 is fixed. So there are now 3 choices here. And I have 2 choices here. So this gives me 6 additional choices. And then if 1 and 2 are fixed, notice that I only have 3 letters left, 3, 4, and 5. So 3 cannot be fixed. And now I have 2 choices and only 1 choice left over there. So there's 2 additional choices. So overall, I have 12 plus 6 plus 2, that's 20 possibilities for one generator, but each subgroup has 2 generators. So if I divide by 2, that is the number of such subgroups. So that is 10. Okay, so there is 10. So in fact, the right answer was 10. There are 10 3-Sylow subgroups. Let's do the same thing for p equals 5 now. Now let's let p equals 5, and I want to find the 5 Sylow subgroups of A5. Again, A5 has 60 elements, which is 4 times 3 times 5. The Sylow Theorems tells me that the number of 5 Sylow subgroups has to be 1 modulo 5, and N5 divides 60. But if N5 is 1 modulo 5 is not a multiple of 5, so it has to be that N5 is a divisor of 4 times 3, 12. The divisors of 12 are 1 or 2 or 3 or 4 or 6 or 12. And the ones that are 1 mod 5, it could be 1, there could be just 1. It cannot be 2, it cannot be 3, it cannot be 4. It could be 6, because 6 is 1 mod 5, and 12 is 2 mod 5, so it cannot be 12. So it's 1 or 6. But I can give you right away 2 different ones. So for example, here's 1, the subgroup generated by 1, 2, 3, 4, 5. By the way, this element is in A5. This is, I can write it as 1, 5, 1, 4, 1, 3, 1, 2. I can write it as an even number, as a product of an even number of transpositions. I didn't check that here, but triple elements of order 3 are also, this is 1, 2, 1, 3. So those are also in A5, in the alternating subgroup. That will be important when I talk about the Two-Sylow subgroups. So this is in A5 because it's generated by an element of A5, and I can just also see what are all the permutations that are here. There's going to be there's going to be the identity, and 1, 2, 3, 4, 5, and then there is going to be a few more, right? Is an element of order, it's a subgroup of order 5, so there's going to be 5 elements of 4 non-trivial permutations. So I can check what are the permutations. So if I do 1, 2, 3, 4, 5 twice, what I'm going to get is 1 goes to 2 and then goes to 3. So 1 goes to 3, 2 goes to 3 and then to 4, or say like 3 goes to 4 and 4 goes to 5. So 3 will go to 5 when I do, if this is sigma squared. 5 goes to 1 and then 1 goes to 2, so 5 will go to 2. And then 2 goes to 3 and 3 goes to 4, so 2 will go to 4. So that's the square. What happens if I do the cubed? To find out what sigma cube is, I have to use this one, but instead of skipping 1, which is sigma, or skipping 2, which is sigma 2, I have to skip 3. So 1 goes to 1, 2, 3, 4. 4 goes to 1, 2, 3, 2. 2 goes to 1, 2, 3, 5. And 5 goes to 1, 2, 3, 2, 3. And finally, sigma 4 is the inverse. So that you just have to read it backwards. sigma backwards, 1 goes to 5, 5 goes to 4, 4 goes to 3, and 3 goes to 2, and 2 goes to 1. So any of these sigma, sigma squared, cube, or to the fourth power would generate the same subgroup. So if I just take any other one that is not in this sequence, so for example here, I can just take 1 goes to 2, 3 goes to 5, and 5 goes to 4. This one is different. This has to be different from P5. So this tells me right away that N5 has to be bigger than 1. There is more than one Five-Sylow, and therefore there's only one option by the Sylow subgroups. It has to be 6 of them. Okay? So we can count again how many permutations are there. So any Five-Sylow will be generated by A, B, C, D, E, right? And there is, well, I can actually start all of them with a 1 because 1 will not be fixed. Nothing is fixed because I have to um, I have to I have to use all 5 letters to get an element of order 5. So 1 is there, and now I can see I have 4 choices for B. I have 3 choices, I have 2 choices, and I have 1 choice. So all in all, what I have is 4 times 3, 12, times 2. So there's in total, there is 4 times 3, 12 times 2 is 24 elements of order 5, but each subgroup has 4 elements of order 5. Each cyclic subgroup of order 5 has 4 elements in it. So I have to divide by 4, which is 6, to get the number of subgroups of order 5. So that tells me exactly that N5 is 6, and that's how it comes about. So let's look at P equals 2, Two-Sylow subgroups now. So now we are going to take P equals to 2. We're looking for the Two-Sylow subgroups of A5. So any such Two-Sylow will have order 4 because the order of A5 is 4 times 3 times 5. What is the number of Two-Sylows? The number of Two-Sylows tells me that it is 1 modulo 2, so that is only telling me that it's odd, okay? But it also has to divide 60. It's an odd number that divides 60, so N2 divides 3 times 5, so it divides 15. So N2 could be 1 or 3 or 5 or 15. Okay, how, well, what are those? Those are all odd numbers, so that doesn't tell me a lot. It has to be one of these 4. Let's see. So my first instinct for a subgroup of order 4 would be of S5. For a subgroup like that, it would tell me, my instinct would say, okay, let's start with 1, 2, 3, 4. However, this is not in A5 because 1, 2, 3, 4, an element of order 4, a cyclic element of order 4 can be expressed as 1, 4, 1, 3, 1, 2. That's an odd number of transpositions, so this is not in A5. That's bad. So are there any elements of order 4 in A5, elements exactly of order 4? So actually, I'm going to claim that no element, if G is in A5, the order of G is not exactly 4. Why is that? Well, suppose that there is such a thing. Let G be in A5 and of order 4 for a contradiction, then G has an expression as disjoint cycles, as a product of disjoint cycles. Okay, so then G will be sigma 1, sigma 2, sigma n, and these are disjoint cycles. And the order of G will be the LCM of the order of each one of those for 1 up to n. Okay, but then if this is 4, then there has to be, I mean, these GIs are these sigma i's. If this is 4, then, and this is an LCM, there is some I such that there is a cycle of order 4, but then sigma I is 1 A, B, C, D, which is AD, AC, AB, which is not in A5. And this is a contradiction because if there was one sigma I that has 4 elements, well, this factorization, when I say that we have proved that any element of S5 has a expression as a product of disjoint cycles, and it doesn't have to be, maybe there are 2 elements that are not in A5, but their product is in A5. But if one of them has already 4 letters in it, it cannot be, it has to imply that G itself is that sigma I, because if there was any other cycle, if you had, say, here A, B, C, D, and then some other cycle EF, I only have 5 letters, so this would not be disjoint, right? So that is a contradiction, which implies that G itself would have to be this element of order 4, a cyclic element of order 4, but this is not in A5, and this was supposed to be in A5, and that's a contradiction. So there cannot be an element of order 4 in A5. So any subgroup of order 4 has to be made up by elements of order 2. So my next instinct would be to try to make a subgroup out of elements of order 2, which is 1, 2, 3, 4, 1, 2, 3, 4. However, these are not elements of order 2 in A5. This is in A5 because it's a product of 2 transpositions, but these are not in A5. So this is not a subgroup of order 4 in A5. At best, I can get a subgroup of order 2 in A5. So it does tell me that this is an element of order 2 in A5. So I can actually, so not this is wrong. I can't use this, but I can get that idea to come up with another one. And it turns out that anything like this, so it turns out that 1, 2, 4, 5, 1, 4, 2, 5, and 1, 5, 2, 4, those are elements of order 2, each one of them. This is isomorphic to Z modulo 2 cross Z modulo 2, so there's no element of order 4. It's okay. And you can check that this is a subgroup and it's in A5. And every subgroup of A5 that is a Two-Sylow has to be of this form. It cannot have any elements of order 2 of this form. All the elements have to be of order 2 of this form, and it turns out that they are all of this type. How many are there of this type? So what I can do is, you see, this has 4 numbers and sort of all the possible permutations. That this one has 1 with 2, 1 with 4, 1 with 5, and this one has 2 with 1, 2 with 5, 2 with 4. So it turns out that all the permutations of 1, 2, 3, 4, and 5 are somehow represented in here. So what you have to have is, out of 5 numbers, I'm just picking 4, and I will be able to arrange them in that way. So there is exactly 5 such subgroups, and therefore n5 is in fact 5, which is 1 modulo 2, and 5 does divide the order of the group 60. So this is the number of of two-Sylow subgroups, and they all look like that for different choices of 4 numbers out of 5. Okay, so those are all my Sylow subgroups. There will be these P2, P2 prime, P2 double prime, P2 triple prime, and P2 4 prime, which is the 5 possible subgroups of this shape in A5. All right, so next, we have already proved the first Sylow subgroup, the first Sylow theorem. So next, what I'm going to do is prove the second Sylow theorem.